Alright, so in this video I'm going to be looking at the parallax method. This is a method for measuring the distance of stars from the Earth that are relatively close to the Earth, somewhere in the distance of what we call 100 parsecs. Although now with satellite-based telescopes, we can actually even get further than that. I'll discuss that later. So we're going to have a look at this idea of a parsec. Where does this come from? The stereo-parallax method for determining the distance of a star, and why there is a limitation to this. Good. So first I'm going to use a diagram here. I'm going to use this diagram here. And what we have here is just a diagram picturing the sun there and the Earth orbiting the sun, and this is 6 months difference, so this could perhaps be, say, in June, and this is in December. Now what astronomers noticed was that stars that are quite close by tend to shift in relation to stars that are much further away. So, for instance, in June, this star over here, would perhaps be very close to this nearby star. So let's call that star A. Would be close to this nearby star. Let's call that N for nearby. And then we may have star B in December. This star. So this star over here seems to shift with relation to the Earth's rotation around the sun. So they decided to use this as a way of measuring the distance of these stars. So what they did was that if we take this distance here, this is called we give the distance from the Earth to the sun. We call that an AU, an astronomical unit, 1 AU. And this deviation from setting up this triangle, this deviation they called P. This is the angle of deviation as we go around, as the Earth orbits around the sun, or a parallax angle. Now, this distance here is the distance from the star to the sun. Now if we take the tan of P, that would equal 1 AU over D. Now it turns out that this angle is extremely small. We actually measured in something called an arc second. Now what that basically means is that you take 1 degree and you divide it by 60 and you get it into minutes, and you divide each of those minutes by another 60 and you get an arc second. So it's 1/3600th of a degree. Now this P was also measured in radians. So we know that for 180 degrees, or let's say 360 degrees, is 2 pi in radians. So if we divide that by 360, we will get the amount for 1 degree in radians, and we've got to divide that by a further 3,600, and that will be in radians 1 arc second in radians, that amount over there. So that's incredibly small, you can imagine that. Now when we look at the tan, when you get the tan of a very small angle in radians, the tan of P basically is equal to P. So we can rewrite this formula as P is equal to 1 over D, and it's this D, they use this to actually define the idea of a parsec, and a parsec is defined. Let me just perhaps move a little bit down here. A parsec is defined as the distance when the parallax angle is 1 arc second. Running out of space. So that is your arcs, your 1 arc second. If this is 1 arc second, then we have that this D is equal to a parsec. Now, a parsec is, I think it's equal to about 3.26 light years. So the closest star is actually a bit further than a parsec. So we can see how small this angle of the parallax method has to be, and this works well. They can use this up to about 100 parsecs. So that's like 0.01 arc seconds that has to be measured. Very, very small angle, and we can see that's why there's a limitation of this. Alright, so you need to be able to use this this formula. It's pretty straightforward. It's not difficult to use, because we have got this P P 1 over P is equal to D, and if you just put this value in arc seconds, your D will come out in parsecs, and you need to be able to convert your parsecs into astronomical units or light years. All right, thank you very much. I hope that makes some sort of sense.